Hello, I wanted to record a video about rotational kinematics so you can get an idea how to solve rotational kinematics problems and how to relate those to linear velocity and acceleration. So let's go ahead and get started. The problem that I chose to do today is 1628. And it states the radius of gear A is RA equals 0.7 inches. So let's go ahead and start with our givens right away. Start up here just listing our givens. Okay, the very first one is that RA 0.7 inches. Okay, and then we have the meshed pinion gear B has a radius of RB. You can see the gears down here. It might be kind of hard to see. Gear A is actually attached to a drive shaft, and then gear B is meshed with it. So as gear A turns, gear B is 90 degrees to it. We turn around this way. So gear B has a radius of 1.4 inches. Determine the magnitudes of velocity and acceleration of a point P. You can see P down here on the propeller. Point P located on the tip of the propeller at the instant T is equal to 0.75 seconds. So we have another given here, T 0.75. The drive shaft rotates with an angular acceleration. A drive shaft is what is attached to A here, and it's rotating with an angular acceleration of root of T. Okay, great. Where T is in seconds. The propeller is originally at rest. We need to put that up here too. So if the propeller is originally at rest, we're going to say that omega A and really omega B naught is equal to 0 radians per second. And the motor frame does not move. That's just telling us that there's no other motion besides what's happening in those gears. So we don't have to worry about a linear velocity of that boat going down. Maybe the boat's chained up or something. Okay, so that's all of the givens that we need. What are we supposed to find? Well, it says it wants the velocity, magnitude of velocity of point P, and the magnitude of the acceleration of point P. Okay, hopefully that gives us a good idea of what we're searching for. So now I'm going to get rid of all that text. We have our givens up here. We have our finds. We're going to jump right into this problem and start doing it. Let's make a plan for this problem. Let's go ahead and make a plan. And you notice that there's a couple different things going on. First off, we know quite a bit about A. We know its acceleration. It's given right here. We know its angular acceleration. That's how much the drive shaft up here is spinning with A. And we also know its initial angular velocity. So we know alpha A, or we can find it. We can find omega A at that time. And then with that information, we know that A is meshed with B. So we're going to have to use the geometry of A and B. So from these, we're going to go to omega B, or alpha B, and omega B. But that's still not the answers that we want. We're not looking for alpha and omega B. What we're really looking for is the velocity on the tip. From alpha and omega B, we're going to go to the velocity of P and the acceleration. So that's just kind of a really rough plan on what we plan on doing for this problem. So let's go ahead and focus on getting started with A. Now, we know that there are kinematic equations for rotational motion. And there's three kinematic equations. The one that we're going to use first is the equation for angular acceleration. And that states that angular acceleration is going to be equal to omega dt. In other words, angular acceleration is equal to the rate of change of angular velocity. That makes sense. That's very similar to acceleration is equal to the rate of change of velocity. We can take this, we can bring the dt on the other side, and we end up with d omega is equal to alpha dt. Okay, so d omega is equal to alpha dt. We have a d omega on one side, a dt on the other. We can go ahead and integrate both sides. The limits of integration depend on what we're integrating in terms of. We're integrating in terms of d omega. So we're going to start off with omega naught. This is going to be omega a naught. And it's going to go to omega. On the other side, I'm going to start at t equals 0 and go to t. Now all we have to do is plug in the equation that we're given for alpha and integrate. The equation we're given for alpha, they say it's the equation of the angular acceleration of the drive shaft. But you notice the drive shaft is connected directly to gear A. So A and the drive shaft have to have the same angular acceleration. Let's go ahead and solve this. On the left-hand side, we just get omega minus, or omega A minus omega A naught. Call this omega A just to differentiate it from omega B. And on the right-hand side, we're going to get it's equal to the integral from 0 to t of alpha, which is 300, times the square root of t. I'm just going to write that as t to the 1/2. Make it easier to integrate. dt. And that's going to be equal to 300 halves over. Okay, to divide by 3 halves, you invert it. Multiply by 2/3, so this ends up being 200. All right, so we actually have an equation for alpha or omega A now. Omega A is going to be equal to 200 halves plus omega A naught. And omega A naught is given to us as 0, so we can cross that one out and say omega A naught, well, it starts from rest, so that one is 0. So we just have 200 t to the 3 halves. At t equals 0.75, which is one of our givens up here, we can plug that in and we can figure out omega A of 0.75 seconds is going to be equal to 200 times 0.75 seconds. Going to be equal to, if you do that calculation, I get 129.9 radians. Okay, so that's our omega A. We also need our alpha A. Luckily, we have an equation for alpha A. We can just plug our t into that, and we'll end up with our alpha A. So our alpha A at 0.75 seconds, that's going to be equal to 300 times the square root of 0.75 seconds. To do that math, that ends up being 259.81. Okay, by using a kinematic analysis for rotational motion, we were able to find omega A, and we were able to find alpha A. We now have those two. Now what we need to figure out is what's happening with B. And the way we're going to do that is we're going to look up here, and we see that their A is actually meshed with B. So if I draw a picture of these, we have A spinning. A would kind of look like this. A little bit more room here. A would be a diagonal gear like this, and it would have a drive shaft. That drive shaft would be spinning in some direction. Okay, then you would have B, which is going to be 90 degrees to that. It's going to look like this. And between those two, they're going to have teeth that are meshed. So between those two, those teeth are meshed together. So they have to move together. What we're going to think of is we're going to think of a little point right here. I'm actually going to call that point. That color didn't work very well. I'm going to call that point C. A little pink point. This is going to be point C. This is gear A, gear B. It looks like I drew them incorrectly because A is actually smaller than B, so I should have made B a little bit bigger. So let's do that. It's actually twice as big as A, which gives us the hint that we're probably going to expect b to be going at half the speed. So what we're going to do is we're going to say, okay, well, the c is actually coming towards me. It's coming in and out of the board as this spins. This one, if it spins to the left as I have it shown, it would come back towards me away from the board. B is also going to be meshed in that same area. So the velocity of C is going to be the same because it's the same point. Those are meshed. What we can do is we can look at one side and we can say, well, I know the relationship between linear and angular velocity. The relationship between linear and angular velocity is linear velocity is equal to omega r. That's the scalar version. If I look at it from the A side of things, on the A gear, I'm going to say the velocity of point C is going to be equal to omega A times RA. Okay, then if I look at the same thing, the velocity of point C, but I look at the B gear, that's going to be equal to omega B times RB. So we have this simple equation, omega A RA equals omega B RB. We know omega A, we know RA, we know RB. So we can solve for omega B. Omega B is going to be equal to omega A RA over RB, which in this case is going to be omega A, which we solved for as 129.9 radians per second. And then we're going to multiply that by RA, which is 0.7 inches. We're going to divide it by RB, which is 1.4. And you can see it just ends up being 129.9 divided by 2. So our omega B is equal to 64.95. Okay, that one wasn't so bad. We got our omega B, and we're going to use that in a minute to get our linear velocity of P. But so far we've done two steps. We've got this one and this one, and now we have omega B. Now we have to find alpha B. Alpha B, we do exactly the same thing. We say the tangential acceleration. Now, be clear that it's not the total acceleration, but the tangential acceleration of point C can be related to alpha times r. You can see that the equation is very similar. The tangential acceleration is equal to alpha times r, the angular acceleration times the radius. Now, we can use that from the A gear and the B gear, and of course, we're going to end up with the acceleration of A. The angular acceleration of A times the radius of A is equal to the angular acceleration of B times the radius of B. Solve for the angular acceleration of B. Which is going to be equal to 259.81 per second squared times 0.7 over 4. This is inches. This is inches. And we get radians per second squared, and it's just that divided by 2, which is 129. Okay, we're getting pretty close to solving the problem now. We have our omega B, we have our alpha B. Now we have to figure out what happens to the propeller. So I'm going to add to my drawing a little bit. If I come up here and this propeller has a drive shaft going up, and then there's the propeller which has blades. Really a lot like a propeller, doesn't it? Anyway, okay, so it has blades, and what we're really looking for is P, which is a point at the bottom of the blades. Now, it's pretty clear that we're just going to use these same equations where the linear velocity is going to be equal to omega times the radius for velocity. We'll do acceleration in a minute. So let's go over here, and we're going to say the velocity of point P velocity of point P going to be equal to omega, in this case omega b, because b is the gear attached to that, omega b times the radius, and this time it's a different radius. It's the radius from the center of rotation out to this point. Now we have to look up here at our drawing. I didn't write that in my givens, and I really should have. So that would be the radius to point P is equal to 0.2 inches. Okay, that's going to be equal to that times the radius to point P, which is going to be equal to WB. We solve for that, 64.95 radians per second. I'm going to get a little bit more room here. And then we multiply it by RP, which we could put in as 2.2 inches. But if you look at that, we're going to end up with inches per second. Typically, we report answers in feet per second. So let's go ahead and change it to feet per second. 2.2 inches times 1 foot for every 12 inches. Inches cancel. And we'll get feet per second. Do that calculation, and we end up with 11.9 feet per second. That's one of our answers, so we're going to box it. Okay, the acceleration, we have to think about actually two components of acceleration. For velocity, there's only a tangential component of velocity, and that's just going to be omega r. But for acceleration, there's both a tangential and a normal component. The tangential component, as we have drawn earlier, tangential component is just going to be that angular acceleration times r. So that one we're going to solve in this exact same way. But we know there's also a normal component. If you remember, the equation for acceleration is acceleration as a vector is going to be equal to omega crossed with r plus omega cross r. Now that's the vector version. The scalar version, we can take both of those and we can say, well, this omega cross r is really just our AT. And the magnitude of that AT is equal to omega r. We know the direction because it's tangential. It's the same direction as velocity. So the scalar version says that AT is equal to alpha r. Alpha times r. That's not alpha sub r. And our AN for a 2D system is going to be equal to omega squared times r, which is the magnitude you get from that cross product. The direction of the normal component in this case is going to be pointing towards the instantaneous center of rotation. So our tangential component would be coming out of the board as this propeller spins. The normal component would be pointing towards the center. That would be our UN, pointing towards the center of rotation. So we need to come up with both of those, and then, of course, the magnitude of acceleration is the square root of the squares. So AT, let's see if I have enough room down here. AT equals alpha, which we already solved for. This is alpha b. This is 129.9 radians per second squared, and we're going to multiply that by r, which was 2.2 inches, over 12 inches per foot. Up with our AT is 23.82 feet per second squared. Okay, that's our AT. Our AN is omega squared r. So our AN is going to be equal to omega, which is 64.95 squared, times r, 2.2 over 12 feet. Up with 773.44 feet squared. Interestingly, and as you probably would have guessed, the component of normal acceleration is much higher than the component of tangential acceleration. The reason for that is the propeller is starting to spin faster, but the centripetal acceleration that it feels is a much higher component. Then we just go ahead and find the magnitude of acceleration, which is the square root of the squares. Square root of AT squared, which would be 23.82. Squared plus the normal component 773.44 squared. Take the square root of the squares. The second one really wins out, and it just ends up being 774. 774 feet per second squared, which would end up being our acceleration. Okay, hopefully that answers some questions that you have. If you have any questions, please let me know. You can come to my office hours, or you can ask me questions on Piazza. Thank you.